Welcome. So in this video we will learn how to determine particle size in an instrument which is based on the principle of dynamic light scattering. So dynamic means that the colloidal particles in a solution are showing the Brownian moment. And these particles are scattering the light. That when a laser is striking the particles, then these particles will scatter the light, and since they are in motion, they are showing the Brownian moment. So this phenomenon is known as dynamic light scattering, and it is based on the principle that the small particles will cause greater fluctuation in the intensity of the scattered light by the detector, whereas the larger particle will show small fluctuations in the intensity of the scattered light with respect to time as detected by the detector. So what is the principle? That the small particles will show greater fluctuation in the intensity, of scattered light, whereas the large particles will show small fluctuations or lower fluctuations in the intensity with respect to time. So here also greater fluctuation with respect to time, and this is the basic principle. And from this intensity versus time graph which will come, we will be drawing the correlogram, that is a graph between the correlation coefficient and the time, that we'll see in the coming slide. And then from that, diffusion coefficient will be determined, and that will be put in Stokes-Einstein equation to have the hydrodynamic size of the particle. Hydrodynamic size of the particle. So all these things we will cover in this video. Main is how to what is the principle of determining the particle size by dynamic light scattering. So as told that dynamic light scattering, dynamic stands for Brownian moment, that is the particles are in motion, that the colloidal particles are in motion because of the collision from the solvent molecules. So they are constantly in motion. So here we can say that the small particles are moving at a faster rate, where the large particles are moving at a slower rate. Here we can see that. So this is the basic principle of Brownian moment, in which the small particles, the Brownian moment is simply defined as the zigzag movement of the colloidal particles in a solution, and small particles will move to a move faster as compared to the large particles, as they are having the more influence from the solvent molecules as compared to that in the large particles. Now these particles again showing that the small particles they are moving faster in the colloidal solution, where the large particles are moving slower in the colloidal solution. And when the laser light will strike to them, and they will scatter the light, and the intensity of the light will be measured. Scattered light will be measured by the detector in the instrument. Now if you see, this is the basic, again the principle is continuing, that if you see the fluctuation in the intensity with respect to time for small particles is higher because they are moving faster in the solution, and large particles are moving slowly in the solution. So intensity fluctuation with respect to time is smaller in this case. This is higher in this case. Now then this intensity versus time graph which has come, that is this will be converted to the correlogram. So this is correlogram, which is a graph between the correlation coefficient and the time, that is in the microsecond. So time is in microsecond. This is the graph between the correlation coefficient and the time. So here we can see that if this is indicating the degree of correlation between the signals, that intensity signals with respect to the times. So whatever scatter signals are coming, so with respect to time, correlation, the degree of correlation that is the showing. So different graph between the correlation coefficient and time, and where we can see that as the time is increasing, the correlation between the scattering signals is decreasing. So obviously, since the particles are moving, that small particles are moving faster, so the correlation decay will be higher in the case of small particles. That is correlation decay. Correlation decay means that if we compare two time interval, that here at one time and another point of time, we see that the scattered signals here and the scattered signals here are not correlated. That is the correlation because the particles are moving. So this intensity, say after some time the intensity will be like this, say. So we can say that the correlation is decreasing. And then since the particle is moving, there will be time that when there will be no correlation at all, and then this is shown here. So at this point of time, that in microsecond the time is there, so at this point of time there is no correlation between the scattered signals with respect to the time. This is indicating, and from this graph we will able to we will able to determine the diffusion coefficient. So here the same is shown in this slide. So here we can see that this is the small particle graph. Small particles are causing greater fluctuation in the intensity of the scattered light with respect to time, whereas the large particles are showing small particles are causing greater fluctuation, whereas large particles are showing small fluctuations or lower fluctuation with respect in the intensity with respect to time. Small fluctuations. So here from the graph also we can say that the small particles are moving faster, the large particles are moving slowly. So small particles, there in the case of small particles, the correlation decay is faster. Correlation decay is faster, whereas in the case of large particles, correlation decay is higher. So again repeating that small particles will cause greater fluctuation in the intensity with respect to time, whereas the large particle will cause small change in the smaller fluctuation in the intensity with respect to time. And these graphs will get converted to the parallelogram, and this parallelogram we can see here that if the small particles is there, so they are moving faster, so correlation decay will be faster in case of small particles. That is degree of correlation between the scattered light signals at different time intervals will be lower in case of the small particle, that the correlation will decrease to a faster rate. In case of the small particles, it will decrease to a decrease slowly in case of the large particles, as is seen from this graph. Now this parallelogram, from this parallelogram we will able to determine the decay rate. That this the for monodispersed, that mathematical model will be created by the instrument, and the for monodispersed particles we will able to determine the decay rate, and from decay rate we will able to know the diffusion coefficient. Now this diffusion coefficient, which is obtained from this parallelogram, will be put into in the equation, which is the Stokes-Einstein equation. This is the Stokes-Einstein equation, and this is Stokes-Einstein equation. So this is the dh is the hydrodynamic diameter is there. It is hydrodynamic diameter. K is the Boltzmann constant, that is a constant, that is its value is 1.38 into 10 power minus 23 joule per Kelvin. Then we have absolute temperature is there, then viscosity, and then diffusion coefficient. So the diffusion coefficient, which is obtained from this parallelogram, will be put in this formula, and then we will have the value of hydrodynamic diameter. Why it is called hydrodynamic diameter? Because not actually the physical diameter of the particle, but it is the it also includes the solvent molecules. That hydrodynamic diameter includes not just the particle itself, but also the solvent molecules. If attached any ions that are attached, stabilizers that are attached to or moving with it, forming a kind of hydrodynamic shell around the particle. So that is why it is called as hydrodynamic diameter. K is Boltzmann constant, which constant value is 1.38 10 power minus 23 joule per Kelvin, and T is the absolute temperature, because obviously the kinetic energy of the molecules in the sample will also depend on the temperature. And then viscosity also, because the moment is again depending on the viscosity. That was these parameters are there in the formula. And then diffusion coefficient is coming from this graph, and we will be able to know the hydrodynamic size of particle, which will be shown by the instrument. Now if you see that the instrument gives these values, this type of graph will come, and then z average will come. That is, z average is the average size of the particles in the solution, and this is intensity weighted average. This is known as the intensity weighted average. It's not the volume weighted average or the average weighted average as was given by the laser diffraction instrument. This is the intensity weighted average, and it is giving more weightage to the large particles. And obviously this z average is shown here. Then comes the polydispersivity index, that is indicating the uniformity of the particles in the solution, uniformity in the sizes of the particle of the solution. So if PD is greater than 0.4, that's this indicates the sample is polydispersed, meaning wide range of the particle sizes are present in the sample. If PD is less than 0.1, then it is called monodispersed. That is the size distribution of the particles is narrow in this case. Okay, then intercept is again indicating the signal to noise ratio. So near to 1 is good quality data which is obtaining. So intercept is indicating the signal to noise ratio, and if near to 1, then it is better. Then again width is again is related to PDI only. So more width means more wide range is there in the particle sizes, or the size of the particles in the solution. So it is indicating that that PDI is less than 0.1 is considered to the sample is considered to be monodispersed, meaning the particles nearly are the same size, and PDI between 0.1 to 4.4, that is giving moderate distribution of the particle sizes, which is typical of many systems. And if PDI is greater than 0.4, then sample is polydispersed, meaning that there is large variety of the particle sizes. This may indicate aggregation or instability in the sample. So that way, PDI value 0.1 to 0.4 is considered normal, and if higher than 0.4 is coming, that this indicates that the sample is polydispersed, or the some aggregation has been taking place. So these are the results which are obtained in the Jita sizer. Jita sizer is the instrument from the Malvern, and it is giving the hydrodynamic science, polydispersity index, and the Jita potential. And Jita potential we will cover in a while.